Hello everyone, my name is Rutika Moharir and here is my final project presentation for 15663 Computational Photography course at CMU. My project is titled Using Light Field Angular Coherency for Depth Estimation. As we can see, having access to the full light field of a scene allows us to create images that correspond to different viewpoints, aperture and focus settings. This project is based on this paper that explores an approach of combining cues from defocus, correspondences, as well as shading for depth estimation. In a scene where the main lens is focused to a point X with a distance alpha star from the camera, the micro lenses enable the sensor to capture different viewpoints represented as angular pixels as shown in the below figure. But how can we exploit this angular coherency? We use the central pinhole image. To share the full 4D light field image in order to refocus it to a depth alpha, we remap the light field as follows, where L is the input light field image, L alpha is the refocused image, and XY are the spatial coordinates, while UV are the angular coordinates. The central viewpoint is located at UV 0, 0. Hence, given the depth alpha star for each spatial pixel x, y, we calculate L alpha star by refocusing each spatial pixel to its respective depth. Hence, all the angular rays converge to the same scene point when refocused as at alpha star. This is known as angular coherency. But since alpha star is unknown to us, we exploit the fact that for the central pinhole image P, where the angular coordinates are 0, 0, the shared xy are independent of u and v. Hence, the central angular coordinate always images the same point in the scene regardless of the focus. This property of refocusing allows us to get constraints from defocus, correspondence, and shading cues. Namely, for photoconsistency in L alpha star, for each pixel, since all the angular rays are converging to the same point in the scene, the angular pixel colors converge to Px of y. For depth consistency, all the angular pixel values should have the same depth. While for shading consistency, L alpha star is viewpoint independent. Following this, the depth estimation pipeline can be explained as follows. The first step is to locally estimate the depth from the defocus and the correspondence cues. These two are used to regularize depth without the shading cues. To improve this depth estimate further, we first estimate shading, which is further used to estimate the lighting. Finally, the lighting, shading, initial depth, and confidence is used to regularize the final depth. Here is the result on a flat image. We can see defocus confidence is high even in the noisy regions, while correspondence provides sharper results. But even after combining both the cues, you can see the initial depth is mostly planar in the low texture areas. However, we can see how the angular coherency helps estimate highly accurate shading and hence detailed depth. Another failure case is specular objects like the image of this bottle. Since the algorithm works on the assumption that we are picturing Lambertian surfaces, the defocus and correspondent response is mostly negligible and hence giving us planar depth. Hence, a possible solution would be to identify and remove the specular component. I tried to implement a simple approach based on the observation that specular pixels will have higher intensities in the estimated lighting. Therefore, our task is to classify every pixel in the lighting estimate as diffuse or specular. One approach is to estimate a confidence measure, that is, high confidence if a pixel is specular along with the lighting estimation. For this, I used a metric known as attainable likelihood measure. First, we remap the lighting estimate to the desired depths. Assuming that the cost here is the lighting at each pixel C x, d is perturbed by a Gaussian noise due to the specularity, we wish to estimate the true lighting L0 at the true depth D0, which does not have the lowest cost after the cost is perturbed. The likelihood is proportional to this. The confidence Cx is then defined as the inverse of the sum of these probabilities for all possible depths. This equation produces a high confidence when the cost has a single sharp minimum and a low confidence when we have several low minima. After measuring the confidence of the lighting estimate, the final lighting estimation is the product of the confidence with the lighting estimation. Here are the results after reweighing of the estimated lighting. Unfortunately, I could not get much improvement. Hence, I plan to continue working on this so that the pipeline can be used for real-world images, irrespective of them being Lambertian or non-Lambertian objects. This is all I have for now. Thank you so much for your attention.